Welcome to video 6. In this video, we're going to talk about chemical reactions, which really are at the core of chemistry, particularly for a synthetic organic chemist like myself. And so we're going to talk about reactions in terms of what they mean, what a reaction is, how we write a reaction out on a piece of paper or on a board or on a PowerPoint slide. We're going to classify various types of chemical reactions, and then we're going to talk about one of the most important things in chemistry, which is balancing chemical equations. So, types of reactions and balancing equations. So, what is a chemical reaction? A chemical reaction is really a transformation in which a substance or set of substances through rearrangement of atoms is transformed into a new substance or a new set of substances. And so, and there is a convention for writing out a chemical reaction when we write it down, and that is we write it from left to right. So there is an arrow, there's going to be an arrow in the middle, which basically means reacts to form. And so what goes on the left side of the arrow are what we call the reactants. So we could call them ingredients, chemicals to the left of the arrow, before the arrow, things that we put into the reaction, things that react. On the right-hand side of the arrow, we're going to have our products. That is the stuff that is produced, the final product of the reaction, etc. So when we write out a chemical reaction, by convention, this will always be the case. Reactants, arrow means react to form or reacts to form, and then products. And so this is, again, this is a convention that reactants always go on the left and products always go on the right. Now, there are various types of reactions, and there are many, many, many types of reactions, but we're just going to look at classifying a few of them, a few different types, and these are the common types of reactions that your textbook classified as well. And if we know the type of reaction that we have, then we can maybe do a better job of predicting what the products are going to be. So if I said, here are your reactants, and this is going to be a single replacement reaction, you might have a better chance of predicting the products than if I didn't say that. Or if I said, here are your reactants, and this is an acid-base neutralization reaction, you might have a better chance of predicting the products than if I didn't tell you that. So what are the types of reactions we're going to look at? The first one is what's called a combination reaction. This is sometimes referred to as a synthesis reaction, although I don't usually use that term, and the particular textbook that we're using doesn't use that term. But a combination reaction is one in which two or more reactants react together to form a single product. And the way another way of thinking about this is that two or more less complex compounds are brought together to form a single compound that is more complex. And we can schematically represent that as A plus B plus C, etc., goes to product D. In other words, two or more reactants forming a single product, that is a combination reaction. And so there are lots of examples of these, the most common probably being the formation of water. So hydrogen gas reacts with oxygen gas to give water. So two reactants combining to give you one product, water. The bottom reaction there is what's known as the Haber process, the combination of nitrogen gas and hydrogen gas to give ammonia gas. Again, you have two reactants combining to form a single product. The flip side of a combination reaction would be a decomposition reaction, and so in that case you have a single reactant that is going to react to form two or more products. And so the products could be elements, they could be the elements that comprise the reactant to begin with, or they could be just other compounds that are less complex. And so we would schematically represent that as reactant A going to product B plus C plus D, etc. So single reactant, reacting to form two or more products. And there are many examples of this. This is a reaction that occurs in automobile airbags, the decomposition of sodium azide to give you sodium metal plus nitrogen gas. So this is the case where a compound is giving you two elements. This is the decomposition of calcium carbonate, which is called limestone, to give you calcium oxide, which is known as lime, plus carbon dioxide. Single reactant. It's a compound. It contains several elements, but it's a single compound giving you two products. This compound, calcium oxide plus carbon dioxide. This happens in explosives, potassium chlorate decomposing to give you potassium chloride plus oxygen gas. Again, a single compound that is the reactant to give you two products, one of which is a compound, one of which is an element. Single displacement. This is also, okay, so before I give you my name for it, this is one in which a single element replaces another element in a compound. So for example, just schematically, compound AB plus element C gives us compound CB plus element A. One way to think about this, and this is how I refer to this, is I would call this the date poaching reaction, right? So A came to the dance with B and left by himself. C came to the dance alone and left with B. Okay, so let's look at some examples of this. This reaction here is what's known as the thermite reaction. I don't know if you've ever seen a thermite reaction, say on Mythbusters or something like that. Aluminum came to the dance by himself, found iron with oxygen. Aluminum goes home with oxygen, and iron is left all by himself. So aluminum is displacing iron in this single displacement reaction. Here, silver sulfate plus zinc gives zinc sulfate plus silver. So zinc is doing the displacing, and silver is being displaced. And this is a reaction that's used to form flammable gases from coal. It's called coal gasification. And so carbon, which is doing the displacing, plus water gives carbon monoxide plus hydrogen gas. Hydrogen is the element that is being displaced. And then you can have a double displacement. This is generally involve ionic compounds, and we'll talk about ionic compounds a little bit later in the series. But you have two ionic compounds, and they just basically switch ions with each other to form two new compounds. So in this case, compound AB meets up with compound CD. They are going to swap. A and C are going to sort of remain the same, but they're going to swap B and D. So the products are AD and CB. So I would call this the date swap reaction, right? A came to the dance with B and left with D. C came to the dance with D and left with B. Some examples of this. These are what are known as precipitation reactions, and we will learn about them in more detail over the course of the school year. But here's an example that lead nitrate plus potassium iodide gives lead iodide plus potassium nitrate. So lead is giving up nitrate and picking up iodide. Potassium is giving up iodide and picking up nitrate. Calcium chloride plus sodium hydroxide to give calcium hydroxide plus sodium chloride. So calcium comes to the dance with chloride and leaves with hydroxide. Sodium comes to the dance with hydroxide and leaves with chloride. So these are some types of reactions. Now the other thing I'm sorry, there's one more type of reaction, and we don't want to forget combustion actually, because it is one of the most significant reactions and a reaction that you'll see lots and lots of examples of over the course of the year. And combustion is essentially a burning. And although the term combustion applies across a lot of different oxidation reactions, it's generally going to be something in which what we would call the fuel, or the thing being combusted, contains either carbon and hydrogen, that would be called a hydrocarbon, or carbon and hydrogen and oxygen, and it's going to react with oxygen to form carbon dioxide plus water. And so the simplest possible example of this would be the combustion of methane. So when we burn methane, which is the major component of natural gas, so if you've got a natural gas appliance in your home, you've got this reaction going on in your home all the time. Methane plus oxygen giving carbon dioxide plus water. This is something that normally doesn't happen in the open air, but it's happening in your cells all the time in a stepwise manner, and that is the oxidation of glucose with oxygen to form carbon dioxide plus water. So you eat glucose-containing foods, you breathe in water, oxygen, you breathe out carbon dioxide, and you sweat out or pee out water. So this is going on inside your body all the time. Combustion of glucose contains carbon, hydrogen, and oxygen, combines with more oxygen to give carbon dioxide and water. So in general, the combustion reactions we will see this year, the fuels or the reactants contain carbon and hydrogen, or carbon, hydrogen, and oxygen. They're going to react with further oxygen to give carbon dioxide plus water. Carbon dioxide plus water. A neutralization reaction is a particular type of double displacement reaction in which an acid and a base react to form water and a salt. We're not going to get too deep into defining what a salt is, but you can see in this case that again, this is a double displacement. H combines with OH to give HOH, or water. Sodium combines with chloride to give sodium chloride. H combines with two H's combined with two OH's to give two waters. Calcium combines with sulfate to give calcium sulfate. So anytime you see a double displacement reaction in which water is one of the products, then that is a neutralization reaction or an acid-base reaction. All right, we want to get on now to talking about balancing chemical equations, which is really one of the most important things we can talk about in any chemistry course. We can write a chemical reaction, but we have to obey what's called the law of conservation of mass, which is that matter is neither created nor destroyed, and we generally, unless we're doing nuclear reactions, which we really won't talk about in this course, we're never converting atoms of one element into atoms of another element, which means we have to end up with the same amount of mass that we started with, and we have to end up with the same number of each type of atom that we started with. And so how can we balance a chemical equation? Because if you look at if I write an unbalanced chemical equation, it will appear as though atoms of certain elements are being created and atoms of other elements are being destroyed. The only way we can balance a chemical equation is by putting a coefficient in front of one or more substances in the reaction. So for example, here's a 6 in front of carbon dioxide, CO2, and a 5 in front of H2. The coefficient has the effect of multiplying everything in the formula by a common factor. So if I say I've got 6 CO2s, that really means in terms of what's going in or coming out of this reaction, I've got 6 carbon atoms plus 12 oxygen atoms. This would mean I've got a total, this represents 5 H2 molecules or a total of 10 hydrogen atoms. The one thing you cannot do in balancing an equation is fiddle with subscripts, these things that tell you how many of each atom are within the compound itself. You can only balance a chemical equation by adding coefficients or by multiplying coefficients. So let's take a look at a very, very simple example, the formation of water by the combination reaction of hydrogen and oxygen. And if you look at this, you'll see that we're violating the law of conservation of mass here, because while we have 2 hydrogen atoms on the left and 2 hydrogen atoms on the right, we have 2 oxygen atoms on the left and only 1 on the right. So this is not balanced because we appear to be making oxygen atoms disappear. So we have to use coefficients to make this happen. And so at this point, I've got 2 hydrogens on the reactant side, 2 hydrogens on the product side, 2 oxygens on the reactant side, 1 oxygen on the product side. I've got to do something about that. So the first thing I'm going to do is increase the oxygen in the products to 2 by putting a coefficient of 2 in front of the water. So that has the effect of balancing the oxygen. But now I've got 4 hydrogen atoms on the product side and only 2 on the reactant side. But I can easily adjust that because I can adjust hydrogen independently on the left-hand side. So if I put a 2 in front of that, that now gives me 4 hydrogens on the reactant side. To match my 4 hydrogens on the product side, I have 2 oxygens on the reactant side. 2 times 1 is 2 oxygens on the product side. I have a balanced equation. Again, I did that only using coefficients, not by fiddling with subscripts. Here's another combination reaction, sulfur plus oxygen. Sulfur exists in nature as a molecule that contains 8 sulfur atoms. Okay, so sulfur plus oxygen to give me sulfur trioxide. So in this case, nothing is balanced, right? I am making sulfur atoms disappear, starting with 8 and winding up with 1, while I am making oxygen atoms appear, starting with 2 and ending up with 3. So I've got to use coefficients to fix that. The simplest place to begin, I think, is to put an 8 in front of the sulfur trioxide. That will allow me to balance my sulfur. So I put a coefficient of an 8 here. I've now got 8 sulfurs on each side. But now I'm really out of whack with oxygen because I've got 24. 8 times 3 is 24 oxygens on the right and only 2 on the left. But again, because this is an element, I can adjust that fairly easily by putting a 12 in front of the O2. And so now I've got 24 oxygens on the reactant side to match my 24 oxygens on the product side. I've got, and as from the previous step, I had 8 sulfurs on each side. So that combination reaction is now balanced. Here's a combustion reaction. Acetylene, so if you've ever operated an acetylene welding torch, which is probably not many of you, but it's something I did when I was young. This is what's going on, the combustion of acetylene gas, which has the formula C2H2. So to begin with, I am unbalanced on carbon, I am balanced on hydrogen, I am unbalanced on oxygen. So I'm going to take the easy first step, which is to put a coefficient of 2 in front of my carbon dioxide. That allows me to balance on carbon. It doesn't affect my hydrogen, so I'm balanced on hydrogen. Now I am unbalanced on oxygen. I've got 2 on the reactant side and 5 on the product side. I'm going to do a little what I call placeholder trick here, and that is to use a coefficient of 2.5 in front of the O2. So now now I am technically balanced. I've got 2 carbons, 2 times 1 is 2 carbons, 2 hydrogens, 2 hydrogens. 2.5 times 2 is 5. 2 times 2 is 4, plus 1 is 5. I'm balanced on oxygen, but you're not allowed in a formal sense to use fractional coefficients like this. And so the simple thing to do is just to multiply the entire operation by 2, which clears the fraction. And if you go through the math here, you will see that I am now balanced I'm now balanced on both sides on all 3 elements, albeit I had to use a fractional coefficient to begin with and ended up with coefficients in front of everything because I had to multiply the whole thing through by 2 to clear the fraction. So those are 3 examples of balancing chemical equations. There are many, many more out there. If you've got Flash on your device, you can go to this wonderful PHET simulation. There are a lot, by the way, we'll look at some other PHET simulations over the course of the year. There is also a worksheet that I have put in the worksheet folder that allows you to not only balance 25 different chemical equations, but then go through and classify all of them by the types that we were talking about earlier in this video. So I am pleased to see that I've come in under 20 minutes on this presentation. So enjoy the simulation and the worksheet, and we will talk to you on the next video.